Okay, so part 3 or module 3 is polynomial interpolation. And we'll be looking at Lagrange interpolation, Newton divided differences, and cubic splines in this particular section. Okay, so what is interpolation? Does anybody know what interpolation is? Okay. So let's say we know the value. That was not spelled right. So we know the value of a function at a set of points. So that set of points, x1, x2, all the way up to xn, with them ordered. So x1 is less than x2 is less than. Okay, so I know f at each one of those values, okay? But what we don't have so we don't have an analytic expression for f of x that lets us calculate values at an arbitrary point. So I don't know. So it's kind of like, let's say the x1 through xn are different times of the month. And then the f is a function that basically tells you what the weather is at that particular time. Now, I don't have a function that tells me how to calculate the weather, but I do know what the value is at the particular x1 through xn. Okay, so this could be a physical measurement. Like I said, temperature, or it could be a numerical calculation. All right. And often, the xi's are equally spaced okay, but not always. That's not a criteria. Okay, so now I have a scenario. Okay, so I know what my function is doing at n particular points, but here's where the interpolation comes in. Okay, so interpolation all right, is the desired x. So, oh, I'm sorry, I skipped something. I'm trying to figure out why my notes don't make any sense. Okay, so what our goal is We want to estimate f of x. All right, for an arbitrary x all right, by drawing a smooth curve through and perhaps beyond the x's. Okay. So now interpolation says, I want to be able to find the function value at an x, but it's in between the largest and the smallest of the data that I know. And extrapolation says, okay, the value that I want to find out about f of x, this x is outside of the domain of between my x's. Okay, so interpolation so that is the desired x is between the smallest and the largest xi's. So interpolation usually gives you a better answer or a better approximation than extrapolation, because with extrapolation, the desired x is outside of my range. So the x's is outside, the desired x is outside the xi's. Okay. So the most common way to model a function is to use a polynomial. Okay. Approximation instead, which is something we're not going to do right now, but we will get to it. That is my hope. Is to find an approximate but very computable function. To use in the place of a more complicated one. Okay. All righty. So the first thing we want to do is polynomial interpolation. All righty. So let's select, we want to select a polynomial. P of X that passes through a finite set of data points. Okay. So by meaning that we're going to find a polynomial all right, P of X that interpolates the given data So this polynomial I'm going to create, P of any xi, is going to be the yi value that the function has already associated with it. I goes from 0 to n, okay? So we're going to have a general polynomial. All right, of degree n. Well, we just got finished talking about this in the last section. That general polynomial P of X is A0 plus A1x all the way up to ANX to the n. And again, AN is not 0. And this is smooth. AN is not 0. This is smooth and continuous. We love polynomials. They are smooth and continuous. Okay. So here's a theorem. It's called the Weierstrass approximation theorem. And Weierstrass is spelled with a W. Okay. If f of x is defined and continuous on the closed interval AB, and epsilon is given, epsilon greater than 0 is given, then there exists a polynomial P of X defined on the interval AB with the property that the absolute value of f of x minus p of x is less than epsilon for all x in the interval AB. Okay, so what does that mean? Something like this. And I have some function, then there's some polynomial, and then I have this. This is f plus epsilon. This is f minus epsilon. Okay, so basically what we mean is given any function f of x there exists a polynomial p of x that is close to f of x over the interval AB. Okay, so that's basically what we're trying to say. All right, so let's say the Taylor series polynomials. All right, these are approximation of a function near a specific point. All right, so these approximate a function near a specific point. Okay, so let's say my function f of x, everybody has seen this example. If you haven't, I would be afraid. So f of x is the function 1 over x, and I want to approximate it. So find an approximation p of x near x naught equal to 1. Okay, so how do we do this? We've all done this. Okay, so I like to do my little chart here. So the first thing I have is n, and then I have the nth derivative. This is the way I teach my Younger students, the nth derivative of x. Then, of course, I have the nth derivative at 1 because that's the point that I'm looking at. So we fill out this chart. And the 0th is just 1 over x, or x to the minus 1, and this is 1. The next one is the first derivative. So the first derivative is minus 1 over x squared. And this is negative 1. And then the second derivative is positive 2 over x cubed. And so this is a 2. And then the next derivative, 3, is negative 3 factorial over x to the 4th. So this is negative 6, etc., etc. Okay. So you keep doing this. We know that this polynomial that we're trying to come up with, Pn of x, is the sum n equals 0 to infinity of the nth derivative at 1 times x minus 1 to the n over n factorial. Okay. So we can find P0 of x. That just says take the 0th term. So that's just f of x naught, which is f of 1. So that's 1. Not a bad approximation. It's actually really not good. P1 of x says take f naught. Says take f of x naught and add f prime of x naught times x minus 1. So this polynomial comes out to be 1 minus 1 times x minus 1. So this comes out to be 2 minus x. So that's a linear approximation. We can find a quadratic approximation. We're now going to get f of x naught plus f prime of x naught times x minus 1 plus f double prime of x naught over 2 factorial times x minus 1 squared. And this one comes out to be x cubed, you write it all out, minus 3x plus 3. Okay. So these are nice, but they're only good. This is only good near x equal 1. Okay, so we can find, so these right here are Taylor polynomials of degree 0, of degree 1, or of degree 2. We can keep going, all right? But again, these are only good approximations. Near x equal to 1. So I may want to find a good approximation somewhere else. Okay. All right. So this is what we want to do. So I say I give you, so here's the problem. All right. So you're given x1 and its y value. x2. Let's start with x naught because I want to start at 0. X naught, y naught. And then we have x1, y1, x2, y2, all the way up to xn, yn. So you can graph these. You can put these little points somewhere on the curve. Okay. So we want to find a polynomial p of x that interpolates the data such that it goes through the data. P of xi is equal to yi. And then then it can give us, we can use that function to approximate what the actual values that we are estimating would be if x was not one of these, but somewhere in between. Okay. All right, so here's our theorem. Given n+1 distinct points x0, x1, all the way up to xn, and n+1 ordinates y0, y1, all the way up to yn, there is a polynomial of degree n less than or equal to n, I'm sorry, degree less than or equal to n, the degree of the polynomial is less than or equal, that interpolates yi at xi, I equals 0, all the way up to n. And moreover than that, this polynomial p of x is unique among the set of all polynomials of degree less than or equal to n. So not only can we find one, but the one we find is unique. All right. Linear interpolation. All righty. So for linear interpolation, we're going to only have 2 points. And with my 2 points, I have some point x naught, y naught. And I have another point x1, y1. And linear interpolation says we are going to draw a line between these two. Okay. So that means that P of X is a line. So P1 of X, because it's of degree of order 1, so it's A naught plus A1X. All righty. Well, we already know that how do you find the equation of a line? You need a point and you need a slope. So I can find the equation of the line y minus y naught. The slope is y1 minus y naught divided by x1 minus x naught. I'll take that and I'll multiply that by x minus x naught. Okay, so P1 of X simply becomes y, but that's just y naught plus y1 minus y naught over x1 minus x naught times x minus x naught. So let's do a little playing around with this. So I know you're saying, why can't we leave it in that form? Because I'm trying to develop something. So I'm going to get a common denominator. So I'm going to get y naught times x1 minus x naught. And then I'm going to subtract off x minus x naught. That's times the y naught. And then that whole thing is divided by x minus x naught, x1 minus x naught. But I still have the other term, which is x minus x naught divided by x1 minus x naught. And that is multiplying by y1. Okay. So now I can simplify this. Yes. So this becomes P1 of X. So now I'm going to get x minus x1 divided by x1 minus x naught. And this value is times y naught. Then I'm going to add to that x minus x naught divided by x1 minus x naught. And this is multiplied by y1. Okay, I think I see a little formula there. Okay, so in the first one, I have x minus x1, but I multiply by x naught. In the second one, I have x minus x naught, I multiply by x1. Oh, that looks pretty good. And alternative construction. So this is what we get. Let me box this because this is real important. So that's for our linear interpolation. We can have an alternate construction And in our alternate construction, we can have A naught plus A1 X naught has to equal Y naught, and A naught plus A1 X1 has to equal Y1. So now I end up with a matrix 1 X naught 1 X1 times A naught A1 is equal to Y naught Y1. Okay, so I can solve that. All right. And when I solve this, this gives me that A naught turns out to be Y naught X1 minus X naught Y1 divided by X1 minus X naught. And I get A1 turns out to be Y minus Y naught over X1, Y1 minus Y naught, sorry, over X1 minus X naught. And then that just takes me right back to that formula right there. So I get the same thing. Okay. So that's linear interpolation. I only have 2 points. So I'm going to draw a line. All righty, let's do quadratic interpolation. So now I have 3 points. So with quadratic interpolation, I now have 3 points. And I'm trying to draw a parabola through these 3 points. So I have X naught, Y naught. I have X1, Y1. And then I have X2, Y2. And my goal is to try to figure out a parabola that fits those. So again, now I'm going to take the easy route because now I figured out that I can do this using that second formula, the alternative formula. So now the polynomial I'm looking for is P2 of X. And this is now A naught plus A1X plus A2X squared. So this is my parabola or my quadratic function. So I'm going to do A naught plus A1X1 plus A2X squared is equal to A1X squared is equal to Y1. And then I have A naught plus A1X2 plus A2X2 squared is Y2. And then lastly, A naught plus A1. I skipped the first one. All righty then, let's move this down. I apologize. Okay. I'm going to throw away this last thing and I'm going to put the one up above it. So now I have A naught plus A1X naught plus A2X naught squared is Y naught. Okay, so those are the 3 equations I get. I love linear algebra. It's one of my favorite courses. This takes us over to a big matrix with 1 X naught x naught squared, 1, x1 squared, and 1, x2 and x2 squared. That is multiplying by a naught, a1, and a2. And that is equal to y naught, y1, and y2. All righty, so we're going to take that thing, we're going to find the inverse of the coefficient matrix. After we find the inverse of it, we're going to multiply it by y naught. So this is like m a is equal to y. So therefore a, which is our vector that we're looking for, turns out to be m inverse times y. Okay. And when we do that and do a little bit of algebra to make it look pretty, we get x minus x1 times x minus x2. Notice I left out the y naught problem, the x naught, and then I'm going to get x naught minus x1 times x naught minus x2. And that is what I am find out to be. That turns out to be very simply what a naught is. And then, oh, nope, I don't want to write it that way. Let me be careful. I'm not writing it the way it was. I'm writing it in a new form. So I have that, and that multiplies y naught. Then I'm going to leave out x1. So I get x minus x naught, x minus x2 divided by x1 minus x naught, x1 minus x2, and that gives me y1. And then the last one, I'm going to leave out x2. So I get x minus x naught, x minus x1. Now I'm going to fill in the denominator with x2 minus x naught, x2 minus x1, y2. Now, let's just pause for a moment. What is P2 of x naught? Well, when I put x naught in, I get x naught minus x1 times x naught minus x2 divided by x naught minus x1 times x naught minus x2. How nice it is that quantity is equal to 1. It gets multiplied by y naught. And notice if I put x naught in the second term, I get 0. And if I put x naught in the third term, I get 0. So yes, I am very happy that P2 of x naught is y naught. Similarly, P2 of x1 will be y1, and P2 of x2 will be y2. So my polynomial does exactly what I need it to do. All right. So we are now to our first major interpolation. And this, why do I feel like I had an A somewhere before? I had an A on polynomial interpolation. So this is little I. Okay, just so I can keep my notes in order. All right, so we did linear and we did quadratic. Okay, so now suppose we have more than 2 points or more than 3 points. Now, I want to call this, we're going to call this I, and this is general interpolation. I have a set of points, xi, yi, I equals 0 to n. And this is going to have a special name. It is called Lagrange interpolation. Okay, so we already saw what, when we had a linear interpolation, what P1 looked like. And then when we did a quadratic interpolation, we saw what P2 looked like. All righty, what we now want to define for general interpolation or Lagrange interpolation, we want to define Pn of x. And Pn of x is defined to be the sum k equals 0 to n of L n k time of x times yk. All right. So the same way we had before, we had all these polynomials. All right. So we have quadratic polynomials here. This Pn of x. Well, the first one is going to be ln 0 of x times y naught plus ln 1 of x times y1. And this is going to go all the way over to lnn of x times yn, right? So now each one of these lnks, all right, is a coefficient polynomial. So Pn of x right now is the nth. This is the nth Lagrange interpolating polynomial. Where, and this is important, lnk is the polynomial x minus x naught, x minus x1, all the way up to x minus xk minus 1. Leave out xk, so x minus xk plus 1. And then you keep going after that all the way up to x minus xn. And then that whole thing is divided by xk minus x naught, xk minus x1, dot, 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 all the way up to xk minus xk minus 1, xk minus xk plus 1, dot, 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 all the way up to xk minus xn. All right, so that is the polynomial. We can also write ln of lnk as, now I don't know if you guys have seen this before, but you know how you can take the sum of a bunch of terms, you can take the product. So pi means the product. We start off at I equals 0, we go to n, but I is never equal to k. And this is of xi, x minus xi divided by xk minus xi. Okay, so this is the polynomial. And what's nice about this polynomial is Lagrange interpolating polynomial is that it goes through every point. And once I know that it goes through every point, I can kind of get a guess for something in between. So let's just say I have something that looks like this. So let's just say, let's just visualize for a moment. Whoa. I'm going to visualize the quadratic as an example. Okay. This is 1 point. This may be another point. And this may be a third point. Okay. And the parabola going through these might be such. Actually, I want to make that go down just a wee bit. Okay. Okay, I may have to move my point, my red point, because it can't have okay, so I got to move my point in order to, it's got to be here. So I can get a parabola. Okay, so that may be my interpolating function. But I can now find, so I can estimate P2 of some z. So if z is here, then I'm going to estimate that P2 of z is this value right there. Okay, so I only knew the value at the other 3 points. So I created a quadratic interpolating polynomial going through that I called P2. And now using P2, I can find the value of something in between x1 and x3. Now, if I tried to find the value of something out here, x4, that would be, if it's outside of less than x1 or greater than x3, I would be extrapolating. But we're not talking about extrapolation, we're talking about interpolation. So I can only look at what I would guess the polynomial would be for values greater than x1 and less than x3. All righty. So disadvantages. I don't have any advantages written first. So this is a great method, but there's some different advantages. There is much work done in calculating. Work done in calculating P2 does not lessen the work for P3. Done in calculating P2 does not lessen the work in calculating So in other words, you literally have to start from scratch to do P3. Okay, so you got to start from the beginning. You can't take what you found in P2 and then try to use it to create P3. It does not work. If I want P3, I got to start from the beginning. Okay, second.
Excuse me, Dr. Long.
Yes.
Do you mean P3 is we have 4 points?
Yes.
Oh, okay.
So P3 would have, so, okay, that is right. So now if I add another point, I cannot use what I did in P2 to help me. I have to start from the beginning. Okay, so if you add a point, so originally we had 3 points, I was able to calculate P2. But if I add a point, I can't use what I did to calculate P2 to say, oh, now I have 4 points. Let's just take what we had and start from there. It doesn't work that way. Okay.
Oh, so we have to recalculate the A0, A1, A2, A3,
Well,
right?
we're not calculating those anymore because we already know how we're going to have to calculate this again. So notice how we calculate so notice how we figured out what P2 was. Here's P2, right?
Oh, yes.
I can't just add on a term for P3, Y3. I have to go back and put in X minus X3, X naught over X3. Then I have to do that to the second term. I have to do that to the third term. And then I have to create a whole nother term. So once I've calculated all of those coefficients and those polynomials, it's a small piece of it that I can use, but really I have to start all over again once I add a new point P4.
Okay, I got you.
Okay. Okay. Okay, and so the second thing, and I think I'm going to end here because we're on down to 2 minutes. So it's inconvenient to pass from one interpolating polynomial to one of greater degree. All right. So sometimes passing from one to another is useful in deciding what degree polynomial I want to use. Okay. So we will pick up on Thursday with an example and talk a little bit about the error. I